Sorry, recorded right?
Yeah. Recording.
Okay.
Yeah, recording. Okay. Yeah.
Okay. So, Bismillahirrahmanirrahim. Let us begin our webinar today by reciting Kitab Al-Fatihah.
Oh.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh, and welcome to the Cataclysmic Management and Sustainable Development CAMSDE Research Group monthly webinar, which is November 2021. Okay, salutations to Dr. Sairahani Leguri Ibrahim, okay, the head of the Civil Engineering Department, Kuliah of Engineering, IIUM. And then to our respected department members, okay, Professor IR Dr. Maisara Ali, Professor Dr. Abdullah Mamun, our academic fellows, IR Izihan Ibrahim and Tuan Haji Badrul Hisham, and as well as to the other honoured members of the department. Last but no in a way least, okay, let us extend a warm welcome to our venerable guest, Associate Professor Dr. Hiroshi Takebayashi, from Disaster Prevention Research Institute, DPRI, Kyoto University, Japan. So today, the Cataclysmic Management and Sustainable Development Research Group, CAMSDE, of the Department of Civil Engineering is honored to be able to host Associate Professor Dr. Hiroshi Takebayashi for his talk entitled of Numerical Simulation Model of Debris Flow and its application to sediment disasters. So before that, let me share a biography about our honorable speaker. Associate Professor Dr. Hiroshi Takebayashi has rich experience in water and sediment hazard research. He started his career as Assistant Professor, Faculty of Engineering, Tokushima University in 2000, and has studied on various research topics such as numerical analysis on debris and mud flows, effect of sediment size distribution on formative mechanism on bed and channel geometries, numerical analysis of bed and channel geometries with vegetation growth, development of bed and channel deformation of software. He is a chairman of IRIC Research Association and a developer of IRIC, which is a free river analysis software and has been developed by Japanese and USA researchers. He introduced two models into IRIC. One of them is two-dimensional bed and channel deformation analysis model, which treats bed material loads and can simulate sandbars, braided channel, and so on. And then the other two-dimensional debris and mud flow models, which and can simulate development process of debris mud flow from surface landslide and deposition process of debris and mud flow on alluvial fan. So at this current position at Disaster Prevention Research Institute, DPRI, Kyoto University, he works on sediment-related disaster and river ecosystem conservation research such as debris mud flow, bank erosion, formation process of riparian habitat, and so on. He also teaches at Undergraduate School of Global Engineering, Faculty of Engineering, Kyoto University, Department of Civil and Earth Resources Engineering, Kyoto University Graduate School of Engineering. With all the experience and knowledge that he would like to share, let us hope this webinar will provide an excellent platform for knowledge exchange between the student and the researchers. So in addition, it can provide a good opportunity to establish networks and collaboration between Kuliah of Engineering, IIUM, and Kyoto University, Japan. So without any further ado, I hereby welcome Associate Professor Dr. Hiroshi Takebayashi to deliver his talk. So welcome, Prof. Okay. Yes.
Okay.
Yes, you can start your talk, Prof.
Yeah. Thank you very much. Thank you for the introduction. Yeah. Okay. I wanna share the PowerPoint. Okay, can you see the slide?
Yes, Prof. We can see.
Okay.
Yes.
Yeah. Thank you very much. So I'm so happy to introduce my research activities here, web seminar. So I have been researching on the sediment transport process in rivers, especially for the sediment disasters in rivers. So and yeah, I'm a chairman of the IRIC. IRIC, we called it IRIC. So IRIC is a software to reproduce the sediment transport process and the bed deformation process in rivers. So today I want to introduce about that model and its application to the sediment disasters. Okay. So yeah, this is the contents of my topic. So first, I want to show you how to perform numerical analysis of debris and mud flow using IRIC. Then next, I want to show you what is IRIC, what is the Morpho2D8. Morpho2D8 is the name of my solver, numerical analysis model. Then introduce basic equation for debris and mud flow analysis. And I'll show you the first two cases of the debris sediment disaster by the local heavy rain happened in Hiroshima in 2014 and 2018. And due to the earthquake, debris flow also happened. So it was happened in Kumamoto 2016 in Japan. I will introduce, I applied our model to this debris flow. Then finally, I would like to introduce about our research institute. Okay. Then, so first, I would like to wait for a moment. I'd like to show you our software. Okay. Wait for a moment. Yeah. More一回かな? Please wait for a moment, sorry. Maybe. Just, I can't just, maybe, okay. Yeah, this is good. Yeah. So this is the software which we developed. It is called IRIC. Then first, okay, I will show you how to perform the analysis of the debris flow. And during my talk, so I'll perform the calculation. Then at the end of my talk, I'll show you the result of the calculation. Okay. So first, I would like to show you how easy to perform the numerical analysis of the debris flow. So first, we have to set the coordinate system. Then I'll try to perform the analysis in analysis of the debris flow, which was happened in Japan, Hiroshima. So in case of the Hiroshima, the coordinate system is the Japan plane rectangular number 3. So I'll choose this one. Then we can import the elevation data through website. Then, okay, this is the Google Earth. Zoom in. Then, okay, wait for a moment. I'm go to the. I try to get the elevation data here. I'll try to reproduce the debris flow of this one. Then I'll try to get the elevation data like this. Now we are reading the data of the elevation. This is the DEM data. I got this one through the website from the Japanese government. Then I'll check on the Google map here so we can load. No. We can load Google image. Okay. Then next, I'll set the numerical analysis grid. Like this. Yes, the width of the calculation region is 400 meters, and the number of numerical grid in transverse direction is 200, and in the longitudinal direction, yeah, about 300 or then, okay. So now, numeric, oh, it takes. Now I could make a numerical grid like this. Yes. Then, so debris flow was happened from here. Landslide was happened here. So I will set the landslide here. Then maybe shape of the landslide is like this. Then depth of landslide. This landslide is very shallow landslide. It's about 30 centimeter. So we set the landslide here. We have to set the maximum erosion depth. So now we do not have the data of the maximum erosion depth. So we give the uniform spatial distribution of the maximum erosion depth. It's about 10 centimeter. It's very shallow. Erosion depth was very shallow. Then next we will set the calculation condition. So choose the debris and melt flow, and end time of calculation is 100 seconds. The computational time step is about 0.01 second. Then calculation result will be output to the file every second. Then on the screen, we'd like to check the hydraulic condition during the calculation. Then next, we have to set more calculation conditions. So for the sediment concentration, we'd like to change the sediment concentration with time, and static deposition sediment concentration. So these are the, I will use the default value. So friction angle is 34, then like this. Then bed material size is 1 centimeter here. Okay. Then save and close. So now I finished to set the all calculation condition. Then we can start the calculation. Okay, so before the calculation, I have to save this file. Okay, then now calculation is already started like this. Then, so during the calculation, so we can check the calculation result at the intermediate time. Then please wait for 1 moment. I want to show you the figure. Yes, good. Yes, wait 1 moment. Yeah, now debris flow has been started from here. Then now calculation time is 1 second. So please wait for a moment. Yes, so yes, now it's 3 seconds. So debris flow is started to flow like this one, like this. Then, okay, so I wanna continue this calculation in the background of my talk. Okay, then I'm gonna go back. No. Okay, I wanna go back to the. How can I stop the eye? Okay. Then I'm gonna go back to my talk. Okay. So can you hear me? Can you
Yes,
hear
Prof.
me?
Yes, Prof. We can hear you.
Okay. So now in the background of my talk, Eric is calculating the debris flow process in Hiroshima. Okay. So I want to introduce about the IRIC. So what is IRIC? So IRIC is a free numerical analysis software of flow and channel deformation. So you can download this software from this website. So it was made for the low cost and high quality river regulation works for rivers all over the world to prevent flood and sediment disasters and to preserve ecosystem in rivers with small budget. For river researchers to perform data deformation analysis easily and deepen our understanding of the phenomena in rivers. So download it more than 40,000 times, and like in Facebook of IRIC exceeded 1,000. So this software is used all over the world now. So IRIC project was initiated by the researcher in USGS, United States of America, and researcher in Japan. Then, so now more than many researchers all over the world join this project from Korea, Canada, Netherlands, China, Taiwan, and many branches. So, and Thailand. So many researchers joined this project. Then they they introduced their model into the IRIC. So many kind of models are available in IRIC. So one-dimensional model, two-dimensional, three-dimensional, and flood analysis model, debris flow, of course. Then, so many kind of models are available now in IRIC. So the name of the model, my model is Morpho2D-H. So I will introduce about the Morpho2D-H. So Morpho2D-H can perform we can perform the horizontal two-dimensional flow and bed deformation analysis using the Morpho2D-H. So not only debris flow, so this model can reproduce the bed deformation process by the wet material load. So in the downstream area, so we can reproduce the flow pattern like this, and also bed deformation process, formation process of sandbar, meandering process. This model can perform such kind of analysis. And this model also can perform the two-dimensional inundation calculation. So like this. Yeah, this location is located near the Kyoto, and about 10 years ago, there was a big flood like this. Yeah, this contour line indicate the flow depth. can you hear me? Are you okay?
Okay.
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 So yeah. So now we cannot see any. but it's okay. Yeah, I'm gonna
Yeah.
continue.
Yeah. Prof, we will open the Q&A session after this session, after you have finished your talk, Prof. Okay?
Mhm.
Okay.
Okay. So, and boundary fitted structured grid can be used by this model, by this software. So, as you know, so river horizontal shape of the river geometry is not straight, so it's meandering. So, in order to get the high result in high accuracy, so we have to fit the numerical grid to the shape of the river, like this one. So for that, all equations are written in the general coordinate system. And we can consider the vegetation in rivers. So vegetation will work as a drag force for the flow, and the sediment will be deposited around the vegetation. So such kind of process can be reproduced by models. So for example, so if we do not consider the vegetation, so long transverse distribution of the water velocity is also uniform in this case. So, but in a real situation, there is a vegetation around here. So if we consider the vegetation, the water velocity becomes smaller in the vegetated area, and in the main channel, flow velocity becomes faster. So, and upstream of the vegetated area, so surface elevation, water surface elevation becomes higher. So these processes can be reproduced. And graded sediment, non-uniform sediment can be treated like this. So yeah, so rivers in Malaysia, so steep, bed slope must be very steep. So in that area, size distribution of the bed material must be very wide. So this model can consider it graded sediment. So I'm going to show you an example of the bed deformation analysis, very short, small examples. We performed the bed deformation analysis in the Mekong River located near the national border between the Cambodia and Vietnam. So this area, so this brown area indicates the deposition area, the green area indicates the erosion area. So this area, so channel deformation is very active. So this area is called the Tanchao area. So we try to perform numerical analysis of the bed deformation for this area. So in this calculation, so if we do these animations show the elevation change, then if we do not consider the vegetation, so flat plain will be eroded very much, and in the main channel sediment deposit well. But if we consider the vegetation, no, like this one. So sediment deposits on the flat plain in the vegetated area. So this is this calculation result reproduce the real situation in Mekong River here. So this calculation result indicates that considering the vegetation is very, very important to reproduce the bed deformation process. And the next animation shows the horizontal sediment sorting with vegetation. So this animation shows the temporary change of the mean diameter of the sediment. So blue area indicates the fine material. So yellow and red area indicates the coarse material. So around the vegetated area, sediment deposits here, then that sediment is very fine. So these models, so we consider the size distribution of the material, so we can reproduce the horizontal distribution, spatial temporal change of the sediment size like this. Mhm. Can you hear me?
Sorry. Yes, sorry. That one is interruption. Okay, you can proceed, Prof.
Okay. Yeah, then this model also consider the cohesive material in the river or the rock bed like this one. Then, yeah, I want to skip this slide. Then, so we perform, we perform the bed deformation analysis concerning the very, very thin cohesive material. That cohesive material layer is located between the non-cohesive material layer. Then, I'll show you the result of the calculation. If we do not consider the cohesive material, so only non-cohesive material, so very beautiful periodical alternate bar will be formed under this condition. But if we consider the cohesive material layer, so the shape of the alternate bar will be changed like this one. So then around here, cohesive material layer is exposed, then there is no erosion around here. On the other hand, at here, so cohesive material layer is already eroded, then the very deep scar is formed like this. So these kind of phenomena can be reproduced by use of the Model 2DH. Then this is the main topics, today's main topics. So Model 2DH can reproduce the horizontal two-dimensional debris and matte flow process like this. So this figure shows the temporary change of the flow depth. It was happened about 5 years ago in Japan. And the sediment deposition dam can be considered in this model. This figure shows the elevation change of this debris flow. So you can find the sediment deposit upstream of the sediment deposition dam. So the function of the sediment deposition dam can be calculated by this model. And houses can be considered. So houses are set by use of the polygon. Then so if we perform the calculation with once again. So in this case, we consider the houses. In this case, we do not consider the houses. So if we do not consider the houses, so debris flow spread like this, and the debris flow fan will be formed like this way. But if we consider the houses and the building like this one, debris flow concentrated along the road very much, then so debris flow does not spread widely. So the flow region is very restricted like this. And the calculation result can be outputted to the Google Earth like this. So we can see the flow process in the 3D image like this. Okay, let me introduce about the basic equation for debris and matte flow analysis.
Doctor, I'm Ayu. Doctor, may I ask question before we proceed with the equation? Boleh tak, Dr. Aifa? May I?
Okay.
Sekejap.
Okay. Maybe okay.
Okay. Is it okay, Prof?
Because if you proceed with the next slide, then after the question, then I can understand better.
Okay. So you want to ask now or You have to ask later.
May I ask now, Doctor?
Okay.
Dr.
Yeah,
Hibashi?
I'm fine.
From your previous slide again, you mentioned that you can indicate layer of soil, right? And also the trees, right?
Tree.
Yes.
Vegetation.
Vegetation, yeah, vegetation. The vegetation. Yeah, how to indicate that in your software? You just because just now you show us that you will you just get the location input the location of the debris flow from Google, and you take everything in Google. So from the Google, and you can you have to indicate the vegetation yourself, or they can trace from the Google just now.
Okay. Oh, okay. Thank you for your question. So, from the Google, we can download only the image and elevation data. So we cannot get the information. So we have to give the parameter. Okay, I want to show you maybe software. It must be better. Wait for a moment. Yeah? Okay.
If I may intercede, I think I can answer a little bit. I think the Google Earth is just a satellite imagery, so you can only get only get the image, as well as probably elevation from SRTM. So for land cover, you need other sort of data. Yeah.
So we have to go to the site and collect all the data, is it?
Not necessary. I think you can either digitize, like I think Prof showed the houses you can digitize by using polygons. Even vegetation also you can digitize. But land cover can be provided by like a soil service, soil maps can be, or land use maps can be, and they've probably already digitized the land cover, whether it's vegetation, whether it's forests or other types.
Or maybe we can get from GIS.
Yeah, GIS
data.
Yes. Go ahead, Prof. Sorry to interrupt.
Never mind. Sharing knowledge. Okay.
Yeah, thank you.
Yep.
Thank you for the explanation. Yeah, that's okay. So, so we have to give the information about the vegetation density or the vegetation height or like this parameter. So then if we measure, if we try to get the DM data, in that case, we always take the DTM also. Then, so we can get the height of the vegetation by the radar. Then, yeah, we go. Yeah, then we go to the field and we also get the vegetation density data. Then install it. Then so something like this. So as explained by the other researcher in your department, so so Google show us only the image. Then maybe so Malaysia government also has detailed DM data, so you can download that DM data also. So of course SRTM will be available, but usually SRTM is resolution is not so high. Yeah, so sometimes we are using that, but even in case of the Japan, so 5-meter resolution DM covered whole Japan area. So we are using that data when we perform the analysis in Japan. Okay, that's okay. More question?
Is it answering
Thank you.
your question, Dr. Ayu?
Yes.
Okay.
Yes, thank you.
Okay, thank you, Prof. And Ayazan for explanation.
Okay, let me continue my talk. So these are the governing equations written in the Cartesian coordinate system. So mass conservation equation, momentum conservation equation, and vector elevation equation. So these equations are for the debris and matter flow, not for the clear water flow, not for the wet material load calculation. So I mean for example here, H is the depth of the mixture of water and sediment. Not the depth of the depth of water, not the water depth. This is the depth of the mixture of water and sediment. Then U is also the depth integrated velocity of the mixture of water and sediment. Not the water velocity, okay? Then E is the erosion rate of the bed. So these equations are almost looks like clear water flow, but each parameter are different from the clear water flow. Then for the vector elevation equation, so there is an erosion rate equation here. So this equation, erosion rate equation is like this. So erosion will be happened, the relationship between the land slope and the equilibrium land slope. Okay. So equilibrium land slope, land slope can be obtained by the constitutive relationship of the debris flow. Then, so when land slope as the equilibrium bed slope, there is no erosion, there is no sediment deposition. But in the mountainous area, so land slope is very steep, then land slope is larger than, steeper than equilibrium bed slope, bed will be eroded. On the other hand, in the downstream area, bed slope is mild, then this value is small. In case erosion would be the minus value, then sediment will be deposited. So land deformation process can be calculated using this equation. Okay, then let me introduce about the difference between the debris flow and the matter flow. Okay, debris flow, it seems very complicated flow and a very large stone and a small stone and water mixture and water velocity is very high. So it seems, maybe it seems turbulent flow, but in the hydraulic, under the hydraulic, so debris flow is not turbulent flow, it's a laminar flow. So because flow depth scale is almost the same as the sediment size scale. So flow depth is a 3 meter, 4 meter, then sediment size is a 1 meter or 2 meter. So turbulence cannot be developed in a flow depth scale. So, okay, so it's laminar flows. So, but when sediment size is very small, so turbulence can be formed on the laminar flow like this way. So upper layer is the turbulence flow and the bottom layer the laminar flow. So in case we called it a mad flow. So when sediment size is very small, so mud flow will be formed like this. Then so in order to calculate the equilibrium bed slope, so we consider the flow depth of the laminar flow like this way. So this model can apply for the debris flow and the mud flow both. So the ratio of laminar flow depth to the flow depth would be is like this way. So when sediment size is large, so this value is almost 1. Then there's a large block around here, but we can also see the very fine material here. So this value would be about 0.6 or something around this value. So it's a mixture of the debris and the melt flow. Then when there is no large rocks and only fine material, so it becomes a melt flow. Okay, these are the constitutive relationships, so energy dissipation equations. So shear stress will be calculated by the solid phase energy dissipation and fluid motion, liquid motion energy dissipation. So for the solid phase, so it is yield stress. Okay. So this yield stress it would be calculated like this one. This is a very standard equation. Then for the liquid motion, so FB friction coefficient can be estimated like this one. So this coefficient is from two phenomena. So one is from the turbulence between sediment particles, the other is the non-elastic collision of the sediment. Then I told you, so I explained to you, so there its flow is a laminar flow. Okay, so but leakage between the particle and the particle, so that leakage can make a turbulence in very small scale. So when we see the flow depth scale, it's a laminar flow. But when we see the very small scale, it's a turbulence flow. So that energy dissipation is considered here. Then this is a non-elastic collision. It's a normal phenomenon. So it can be happened in the debris flow. So then we can calculate the energy dissipation, then perform the analysis. Then we can also consider the phase change of the fine sediment. So what is the phase change? So as you know, so liquefaction of the sediment, so during the earthquake, so same phenomena can be happened in the debris flow. So fine, very, very fine material will behave as a liquid phase, so with water. So very, very fine material, the material is smaller than 0.02 meter, 2 millimeter. So we treated it as a liquid. Then the mass density of the liquid becomes increased because the fine material included into the water. Then so this value density of the liquid is not 1, 0.38 or 0.16, so it's larger than the 1. Then so when mass density of the liquid phase becomes larger, so equilibrium bed slope becomes much more smaller. So debris flow can be transported downstream more. So with a mild slope area, sediment can be transported. So anyway, so in the debris flow, liquefaction is also happened. Then we considered that phenomena in this model. And as I introduced to you, so we would like to use the not straight numerical grid. So we'd like to use a boundary fit numerical grid or the meandering shape numerical grid. So all equations are transformed to the general coordinate system. Then, so because, for example, when we use the Cartesian coordinates at the boundary between the wet area and the dry area, so numerical friction will be happen, the flow depth becomes larger, and so we would like to avoid that phenomena as it possible. Okay. Then so these metrics will be used to transform the convert the equation. Then For example, so this is a mass conservation equation. So in Cartesian coordinate system, then we will use these metrics. Then we can get the equation in general coordinate system like this one. So if we convert if we consider these if we change the coordinate system like this one, momentum conservation equation becomes like this. It seems very, very complicated, but the characteristics of these equations are the same as the original one. So this is a shallow flow equation. So, but it seems very complicated like this. So we are solving this kind of equation. Then, so this is a test case of the mad flow calculation with a very, very highly meandered channel. So this is very strange shape, but as a test case, we perform the calculation like this. So at the boundary, phenomenon is much more smoother. So it might be better. Okay, we can get the calculation result with high accuracy. Okay, let me apply this model to the sediment disasters in Hiroshima 2018. So Hiroshima is located the west part of the Japan. Then the very big sediment disaster was happened in 2018. Like this. Okay. So landslide what happened around here, here, and also here. Then this debris flow will be propagated to this way and also this way. So I'm going to show you this one. Around here, so there is a channel here, okay, erosion area here. So this debris flow will be flow to this way and this way. The other one is also flow to this way and this way, like this. Another one is flow this way. Okay. So very complicated debris flow. Okay, around here, so there is some houses here. So these houses located higher land elevation area. So some sediment are flown into the garden or the road, but the houses didn't have any damage. So main debris flow into this lower channel. So, but this area, so debris flow in this valley is much more larger. Then you can see the very huge rock with diameter is about 2.5 meter or something. Then around here, there are many houses, but all of the houses are completely destroyed. And this house, first floor of this house is also damaged. Okay, this is the image of the flow path of the debris flow from the air. Then, and this is the main valley debris flow was happened. The debris flow was flowed to this way and this way, then goes downstream. So as you can see, debris flow along the road. So this is a very important. So this result indicates that we have to consider the houses to estimate the flow path of the debris flow. Yes, so and around here, so there was many houses around here, so all of the houses are completely destroyed, and the sediment flow around here, but this house has no damage. Okay. Then here, so there is a house here. Okay. Then this is the second floor of the houses. First floor is completely disappeared. So Then, as you can see, this house is broken. That had a big damage. But then first floor is completely disappeared. But the damage of the second floor is not so severe. Yeah, severe. So actually, the person who was in the second floor was alive. But the person who was in the first floor is dead. Okay, was dead. So flow depth of the debris flow is not so deep in the residential area. So flow depth of the debris flow cannot be 20 centimeter, 40 centimeter, no. So only 2 meters, 3 meters, so flow depth. So damage of the second floor is in generally not so severe. The debris flow along this road. So flow along this road. As you can see, first floor had a damage, but the second floor almost no damage. So people do not escape to the other area. If people escape to the second area, no problem, they can arrive. So this is the same case. It's the end of this road. So the debris flow to this way to then go to this way, like this. Okay. Then so this is the same case. The first floor had a damage, but the second floor almost no damage. So if the people escape to the second floor, they can arrive. Then at the downstream area, a lot of the sediment was reported. This animation shows the spatial temporal change of the rain intensity. So as you can see, line shape large rain intensity area is formed like this way. So okay. Then please focus on this area. Then large rain intensity area flow to the northeast. So, but new large rain intensity area is formed at the downstream, southwest. So, at this red point area, so high rain intensity is continued long time. Then sediment disaster what happened. Okay, this one shows the temporary change of the rain intensity. The maximum rain intensity was recorded at 6 p.m., about 7 p.m. The debris flow was happened at 8 p.m., 20 o'clock. So the rain intensity at this time is very small. So maybe the people in the residential area could not, they thought maybe the rain is almost stopped, so we can save. But that means debris flow what happened. Okay. So debris flow, sometimes debris flow will be happened before or after the maximum rain intensity. It can be happened very often, so it must be very important information. Then so I'll show you the result of the analysis. So we set the 3 slope failure landslide, shallow landslide here. Then perform the calculation. Then now so we do not get the information about the timing of the slope failure. So in this calculation, so we assumed that all slope failure happened at the same time. This is the result, a comparison between the numerical analysis result and the field observation. So as you can see, the flow area of the debris flow can be reproduced by this model well. Okay, let me show you the temporary change of the flow depth by the debris flow here. So in Japan, government set the sediment disaster warning area like this way. So, but the debris flow does not spread in yellow zone well. So because this warning area is obtained, do not consider the houses and road. So when road and houses do not consider, maybe the debris flow will be happened. Debris flow will be inundated widely like this way. But in a real situation, so there are many houses and road. So debris flow region will be restricted very well. Okay. The travel time to the residential area from the landslide area is 50 seconds. So 50 seconds must be very short time for the escape. So maybe people cannot go out, go far from the houses. They cannot go to this area. So as I told you, damage of the second floor is in general very small, but 50 seconds would be enough to escape to the second floor. So we recommend the people in the residential area, please escape to the second floor. So sometimes, second floor will be damaged. Sometimes completely house will be completely disappeared, completely broken. So, but in many cases, so second floor will be very safe. Okay. Then this red area, brown area, blue area. So these areas, so there is no debris flow because land elevation is slightly higher. So debris flow will flow to the very low elevation area only. Okay, let me show you another example of the debris flow disaster. It is also in Hiroshima. It happened in 2014. So at that time, also line shape high rain density area was formed like this way. So heavy rain continued very long time. And this is a geological condition, geological condition map. So this granite will be distributed very widely. So that means a very fine material will be produced well. So like this one. Wait for one moment. Yeah. Sorry. So it was obtained by the drone UAV like this. So very large rock are transported to the downstream area, and also wood are transported to produced very well. Okay. Then I'm gonna show you here. Okay, like this. Then so these houses, half of the house is completely destroyed, but the other half is exists like this. So debris flow float around this area and also this here. Then please look at around here. So behind the building, so there is no debris flow. Behind the building, there is no debris flow. So that means that if the people escape to this way, they can arrive. So this is a very important information. So behind the big building, so debris flow cannot come. So people do not escape far from their residential area. Only 20-meter walk, they can arrive. So this is a very important information. Yeah. Okay. So we also performed the numerical analysis for this debris flow. So this debris flow also 3 landslides was happened. Then we performed 2 calculations. So calculated result almost same result I already introduced you. So with the house case and without house case. Then yeah, like this one. So we consider houses. The comparison of the inundation area of the debris flow. So near the residential near the valley, so we can find a very big rock and wood and also fine material. But the downstream area, we can see only the fine material. Then this brown area indicates the sediment deposition area of the large rock and driftwood. Then our model can reproduce this distribution. So like this. So reproducibility is not so bad, I think. Okay. This animation shows the temporary change of the flow depth. This animation shows the temporary change of the erosion and the deposition thickness. So upstream of the houses, so we can find many sediment deposition. So sediment deposits in the upstream area. So in the downstream area, sediment discharge becomes smaller with time. So considering the houses, so damage area of the debris flow becomes very small. So in order to estimate the damage of the residential area, considering the houses must be very important. Okay, yeah. This animation I already showed you, so I want to skip this one. Then please focus on this yellow area. So when we do not consider the houses, this area, yellow area, we judge this yellow area will be damaged. But in the real situation, if we consider the houses, this yellow area, there's no debris flow here. So if we make the excavation area around here, so that must be fine. They can escape easily. Okay, and then this model can consider. Then I want to introduce about the debris flow characteristics. So as you can see, debris flow becomes larger and larger with time, like this. So when landslide was happened, debris flow is very small, but the volume of debris flow becomes larger and larger with time because in the transport process of the debris flow will erode the sediment, erode the bed, then eroded material will be introduced into the debris flow itself. So debris flow becomes larger and larger with time in the transportation process of the valley. So this phenomena must be very important to manage and to make a countermeasure of the debris flow. So in this case, sediment production by landslide is only 2,000 cubic meter to the 3,000 cubic meter, but sediment flowed into the residential area. The volume is 34,000 cubic meters, so it's 10 times more than the landslide volume. So this figure shows the longitudinal distribution of the total sediment discharge. Okay. So usually government try to construct the sediment deposition dam near the residential area at the downstream end of the valley. But if you make if we make the land sediment deposition dam here, we have to make a very big sediment deposition dam because the sediment discharge is very large. If we construct the sediment deposition dam here, sediment discharge is only 3,000. In this case, small sediment deposition dam, sabo dam, can stop the debris flow. So, but if we construct the sediment deposition dam here, we cannot catch the sediment from the tributary. So if we set the sediment deposition dam here, so total sediment discharge is only 25,000 cubic meters. So that means smaller, much more smaller sabo dam, sediment deposition dam will work to stop this debris flow. So there is no way, there is no reason to construct the sediment deposition dam at the downstream area. So if we can construct in the upstream area, so small sediment deposition dam is okay. So we can save the construction cost. Okay, finally, I wanna introduce about the debris flow due to the earthquake which was happened in Aso, Kumamoto, 2016. So a lot of landslides were occurred in Aso area, Kumamoto, Japan, due to earthquake on April 2016. The collapsed sediment were fluidized in San-no-dani River basin and were transported to the downstream area as debris flow and mud flow, in spite of no rain. So the most of the landslides were occurred at the same time because the earthquake was external force to the cause the landslide. So this is a large difference between the debris flow by the flood, heavy rain, and the debris flow by the landslide, earthquake. So in case of the earthquake, landslides were occurred at the same time. As a result, the multiple debris flows joined and developed well. So in this research, numerical simulation of the debris flow due to multiple simultaneous surface landslides which were occurred in San-no-dani River basin and the effect of multiple simultaneous surface landslides on the flow characteristics of the debris flow is discussed. Additionally, the effect of the water saturation ratio on the flow characteristics of debris flow is discussed. This is sediment damage and the phenomena of the sediment disaster. So during this earthquake, 57 debris flow was happened at 10 landslide and 123 cliff failure. And human damage is 50% was dead by this sediment disaster. Okay, San-no-dani River basin is located in the Kyushu Island, central of the Kyushu Island. This is the Aso Mountain. Then San-no-dani River is the main channel of the San-no-dani River is this one. Okay, so in the mountainous area, there are many landslides, but what happened? Erosion area is formed. Then mud flow, sediment is inundated like this. So earthquake what happened April 16. Then before this earthquake, so almost no rain, but debris flow and mud flow was happening. So it was seems very strange because there is no rain, there's no water, but debris flow was happening. So because volcanic ash of the Aso mountain contains water very much. So even in the sunny days, the porosity, no, so water is filled with the, no, so I'm sorry, below that, in the land, water is filled with the void area. So usually, so high water content is continued, is kept in this area. So landslide, no, I'm sorry, debris flow and mud flow was happened. Okay. Yeah, so in the mountainous area, so there's no surface flow, but in the downstream area, there's a surface flow. So that means that in the mountain, there's a lot of water. Then this is a sediment produced by the mud flow. So it's a volcanic ash that contains a lot of water. The volcanic ash in river basin has high water retentivity. Okay, this is, okay, there's a house around here near the bridge. So then this house was attacked by the mud flow like this. Then there's a bridge here. So then just after the mud flow, this river is clogged due to the large boulder. There are two large boulders here, like this. Okay. So this bridge is stuck, clogged. Then mud flow will be inundated very much. Then damage to the houses very much. In the upstream area of this inundation area, so there is a Sabo dam. There is a sediment deposition dam. So this dam deposited half of the produced sediment like this. Okay, so we performed the numerical analysis of the mud flow by the earthquake. Then we try to consider the water content in the land. So we try to change the mass conservation equation like this one. So because if the water content is very low in the land, so when land surface is eroded by the debris flow, but supply of the water is very small. Only the sediment is introduced into the debris flow. In that case, debris flow will stop soon, but land is filled with the water. Then in that case, so eroded sediment contains a lot of water. Then debris flow continue to flow to the downstream area. So we try to consider the rate of the water content. Okay, this is a calculation condition. So yeah, we performed the analysis using for this area. Okay. Then, as you can see, a lot of landslide was happened. Then we set the small landslide at the upstream end of each erosion area. Then these landslides was happen at the same time in this calculation. Okay, so in case 1, so I'll show you the temporary change of the flow depth. The condition is the saturation. The land is saturation by water, and multiple these landslide was happen at the same time, like this. Then these landslide so change to the debris flow, they flow to the downstream area. However, they are stopped. But the main channel of the debris flow continue to transport to the downstream area. Then big damage was happen at the downstream area. So debris flow can be transported to the downstream area without surface water. Okay. So in this calculation, we do not consider surface water flow. However, we assume the saturation condition by the water in the land, so debris flow, mud flow can be transported to the downstream area. So this is the elevation change, horizontal temporary change of the elevation change. And the sediment deposits around here, here, and here because there's a subodam here. So then when sediment deposits around here, so intermittently debris flow will stop, then flow to the downstream again like this. Then these debris flow could not merge to the main flow of the debris flow. So these are the stopped around here. They didn't transport it to the downstream area. So in case 2, we use a saturation condition, but we consider only one western slope slide. So in this case, mud flow will stop here. So because there's a subodam here, then debris flow will be stopped here. So if only one landslide was happen, not multiple landslides, so mud flow cannot transport it to the downstream area. So considering the multiple landslide must be very important. So location of the landslide must be also important. So if we consider only the northern slope landslide, this debris flow, the scale of the debris flow is small, but can be transported to the downstream area. So because the travel distance is much more longer, so then erosion, debris flow, mud flow can be developed before the subodam, so can transport it to the downstream area. Like this. Okay. Then in this case, so we do not consider phase change. So I mean the fine material does not behave as a liquid. Fine material behave as a solid particle. Okay. In this case, mud flow cannot transport the downstream area. So phase change must be very important factor to simulate the mud flow. Okay. Then if we assume the 50% saturation of the water, so mud flow cannot transport it to the downstream. Well, so stop around here. Then so saturation must be very important. So in case of the Kumamoto, so this mud flow, so before the earthquake, so there is no rain. So 1 week there is no rain. So but this material, volcanic ash, can contain the water long time, can keep the water long time. So in these kind of places, so by the earthquake, mud flow can be happened. Okay. Main part of my talk is that also. Finally, I would like to introduce our research institute, Kyoto University. Okay. Kyoto is located in the west part of the Japan. Then Kyoto is one of the most beautiful places in Japan. I think that you can enjoy the Kyoto sweets very much. And you can also see the Maiko-san like this one. The DPRI Kyoto University, located in the Kyoto Prefecture, and Kyoto University has 3 campuses: Yoshida campus, Katsura campus, and Uji campus. So DPRI located in the Uji city, south of the Kyoto city. There are many researchers at DPRI, about 100 faculty staff. So they have been researching on the earthquake and the collapse of the structure about earthquake, volcanic eruption, flooding, tsunami, typhoon, debris flow, liquefaction by the earthquake. So we try to cover all disaster. Okay, then we are welcome to come to Kyoto University to get a PhD or for the collaboration work. So our government prepared the scholarship, and through Kyoto University you can apply the Monbu Kagakusho Japanese government scholarship. So if someone wanna study the debris flow, study the sediment disaster calculation technique, and someone who want to clarify the sediment disaster phenomena, so please try to get scholarship, then apply the scholarship, then come to Kyoto. It's very happy for us. So now, so as you know, so the situation is very severe due to the COVID-19, but maybe from the next year, so we can go abroad, then we can go visit each other, then discuss the sediment disaster, or discuss the transportation process of the sediment in river, well, in near future. Okay, thank you very much. So if you have any questions, so.
Okay. Okay. Actually, Prof, we have our postgraduate student, okay, in this seminar. So I hope that all of the students, if you are plan to further your study for PhD, so you are welcome to apply for that scholarship, right, from the Kyoto University. Okay. Okay. So thank you very much, Associate Professor Dr. Hiroshi Takebayashi, for his good sharing knowledge and very informative. Okay, a lot of knowledge.
Sorry.
Yeah.
Sorry.
Yeah.
I completely forgot to show the result of the numerical analysis.
Oh, okay. You want to show?
Yeah, I want to show.
Okay.
Wait for a moment.
Okay.
Just yes. Yeah, good. Okay. So during my talk, this calculation was completed. Okay. So this is a temporary change of the flow depth of the debris flow, which had happened in Hiroshima about 10 years ago. Okay. So like this. So from the setting of the calculation, the setting making a numerical grid, then get the calculation result is only 1 hour or 2 hours, very short time. So so after the disaster, so we have to give information to the government in a very short time, quickly. So we try to develop. So we are using this software to perform the analysis, then give them the information about how much of the sediment was produced, and what we have to do next. So this kind of, so in order to give information to the government. So this short time calculation must be very powerful, we think. Okay. So like this, so calculation must be very easy. Okay. Then so we hope you too use this software for the river flow analysis and sediment disaster analysis. Okay, thank you very much. Sorry.
Okay. Thank you very much. Okay, Prof. Takebayashi for his good sharing knowledge. Okay, for his good sharing knowledge, and very informative. Okay, so we have learned a lot today. Okay, regarding to the new knowledge. Okay, and then the condition of earthquake in the Japan itself, and also about the software itself. Okay, how that software can produce an analysis to estimate the debris flow and so on. So now I open the Q&A session to all audience to ask any question to our speaker. Okay. Anyone to ask? Anyone would like to ask Prof. Takebayashi regarding to our webinar today? Okay.
I have one question.
Thank you.
Good morning, Dr. Hiroshi. Just now you mentioned using the software Morpho 2DH, and you showed us on the bed deformation. It's more on the bed erosion. But I do wonder, can the model can look into bank erosion, river bank erosion? Because when I look at the model itself, it is only looking at the lateral or horizontal movement of the sediment. But can we also use that model to look into the erosion of the riverbank?
Yes, this model can consider the bank erosion process. Then so, but if the bank is located in the middle of the calculation area, yeah, we can consider the bank erosion process. So channel deformation process can be reproduced by this model. Then so IRIC has another model, so NICE 2DH, which was made by Professor Shimizu and I, collaborated, developed one. So that one can consider the temporary change of the numerical mesh. Okay.
Yes, yes.
So the development process of the meandering can be reproduced. So if you access to the IRIC website, so you can see that animation. Yeah.
So it is in the website.
In the website, yeah.
I see.
You can see that animation. So, or yeah, if you send me an email, I'll send you the animation.
Okay.
So anyway, so this model can consider the bank erosion process.
I see. Okay. All right. I have another question. I'm not really an expert in debris flow whatsoever, but you did mention that for debris flow, it consists of the water and also the fine sediment. Do you consider the movement of larger items like rocks, tree logs, and so on into the model?
Yeah. So, yeah, this model considers both large rock and fine material. So, but how can I explain? So, yes, so when we, for example, so I show you the debris flow in the Hiroshima. In that case, so very large rock, 1 meter, 2 meter, then in the debris flow. Then so we consider that information, very large rock, as an information of the diameter of the sediment. So diameter of the sediment is a parameter of this calculation. So large rock and also fine material both are considered in this model.
Okay, so it depends on, I mean, the parameter that when you input into the software, you include the size, right? So that size indicates the items, the larger items. Okay,
Yeah.
all right.
So, of course, we cannot simulate the behavior of the each sediment.
Differently,
We cannot.
yeah.
So this large rock move to where we cannot reproduce, but yeah, so this is a constitutive model. So yeah, so but that information, so large material will be considered as the information of the sediment size.
Okay, all right. Thank you, Dr. Hiroshi.
Thank you.
Okay. Another questions from the audience?
This is not, yes, so Taifa, this
Okay.
is not really a question per se, Prof, but maybe I would like to share. This is a video of a debris flow that happened in Japan, I think back in July. Yeah? So because I think for us in Malaysia, it might be difficult for us to sometimes visualize how this debris flow look like exactly. But if you can allow me to share with you for just a minute.
Okay, Ken.
No problem.
I'm sure you're already aware of this, Prof. This one that happened in Shizuoka. But okay, so.
Shizuoka case.
Yes.
Yeah, so yeah, that one.
In what year, Dr. Dani?
So yeah, of course I have this video. Then I got the permission from, yeah, this is a very big one. This is a mad flow.
Okay.
So the numerical simulation of this mad flow is already finished. Then if you want, I can show you now. And so then there are many video. There are many video in Atami Shizuoka case. Okay. Then so based on that information, so we try to reproduce a phenomena with a high accuracy. So anyway, so to get the video of the mad flow is a very, very rare case. Rare case. So yeah, so this Shizuoka's case was very nice for researcher. Yeah.
Okay.
Yeah.
So from your modeling, was the Shizuoka case any different, or was it unique in any way compared to the to the other occurrences that you have studied so far, perhaps?
So Shizuoka's case is a very, very rare case. So, but yeah, it's a very important phenomena, and fortunately we could get a lot of information, video. So we are using that. We collect a lot of video, then using them for our research. Okay. So if you want to see them, so we can show you.
Okay, thank you, Prof. Thank you.
Okay, thank you, Dr. Dani. Okay, and then I have two questions, Prof. Takebayashi, regarding to your slide number 2. Can you show to us slide number 2?
Number 2, né? Okay,
Yep.
wait for a moment.
If I'm not mistaken, slide number 2. Yep.
But wait for a moment.
Yep.
Go to
So
number 2.
yep.
This one?
1, 2, 3. So what is the difference between 1, 2, 3 dimensional model? Can you explain more, Prof? Yeah. 1, 2, and 3 model. Yeah. Can you explain more about this different? What is the difference between these 3 types of the model?
Okay, thank you very much. Today I introduce about the two-dimensional model of the debris flow. So two-dimensional is, so today's case is a horizontal two-dimensional. So like this one. Okay, so this is a view from the air. from the airplane. Then so here is the upstream, so here is the downstream. Then this is the left bank. This is the right bank. Okay. Then so in two-dimensional model, so it's we are using the depth integrated value. So we do not consider the velocity in the vertical direction. So, however, in the three-dimensional model, so we can consider both the all flow direction, vertical, longitudinal, the transverse flow velocity can be reproduced, can be considered. So then, so this maybe this figure is not clear. So it is very difficult to understand this figure. So, but yeah, so this is a cross section. In the cross section, so transverse velocity and the vertical velocity is reproduced. Then there is an eddy here, like this one. Therefore, in the one-dimensional model, so this is a longitudinal distribution of the land elevation. So each point is a land elevation in one cross section. So here the upstream, here the downstream. So we can see only the longitudinal distribution of the flow. So in one-dimensional model, we do not consider the flow to the vertical direction and the transverse direction. We don't consider. We consider only the from upstream to the downstream direction water velocity. So the water surface elevation, water depth information, bed elevation information, only one in one cross section. Then see only the longitudinal distribution. So this is the one-dimensional model. The two-dimensional model, as I told you, so we can see the horizontal distribution of the velocity, water depth, but don't consider the vertical direction.
A variety
So
of parameters. A variety of parameters. Yep.
Yes, something like this. No? Do you understand?
Okay, understand. Okay.
Okay.
Thank you very much. Yep.
Okay.
And the other question is, you said just now, okay, in order to use that software, we have to use two different conditions, like with house and without house. Okay. So with house and without house, right?
Yeah.
Okay. So is there any consideration or factor instead of these two factors that we can use, okay, in order to analyze by using this software?
Okay, so in order to, so when we consider the houses, so okay, I'm gonna show you the software.
Yep.
Okay, for example, okay, so for example, there is a parameter here, fixed bed elevation. So, or for example, there's an obstacle. So, for example, if okay, wait for a moment. Okay, there's a house here. Okay, there's a house here. Okay, we can add polygon here. Then obstacle. Then now there's obstacle here. Then so we can reproduce we can consider the houses like this way. Then so if we consider the height of the house, so we set the fixed bed elevation in 0. For example, okay, here, here, here. Then we can input the height of the houses, for example, 6 meters. Okay, so in this case, houses which the height is 6 meters is set here. Then so if the flow depth is deeper than the 6 meters, so debris flow will overflow these houses. Okay, so something like this. So we can consider the houses by making a polygon like this. Then, so in case of the Japan, so this polygon is already prepared by the government. Then we can download the house information from the website of the government. Okay. Then, yeah, sometimes we are trying to use that polygon, that information.
Okay.
Then, yeah, so if we do not have that information, we are making the polygon like this.
Oh, okay. So this is how you estimate the one. Okay.
Yeah.
All right. Okay. Thank you very much, Prof, for your explanation. Any other comments from the researchers and also the student? Student, you would like to ask to the Prof?
Prof, I have a question.
Okay. Proceed first.
Prof, I want to know the free version that you mentioned just now. Okay, that is the full version, or we need to buy the complete version, or the one that available, the free version available, is it the complete version, or we still need to buy in order to get a complete version of the software?
Sorry, I do not understand completely, but maybe so. Yeah,
full version. I mean,
free
Yeah.
software.
the one that available in internet end. Is it the full version?
Yeah. Full version.
Full version.
Full version.
Full version for free, Prof.
Full version is available.
For
Completely
free. For free.
Completely free. I thought to have a full version, then we need to buy the software,
Okay.
or you just give part of the software, then the rest you need to buy. No, lah.
No need to buy. No need
Okay.
to buy.
Okay, we can use it freely.
Freely and full version, right, Prof? Okay.
Full version available.
Okay.
Yeah.
So let's download for free.
Free.
Okay. So
if we have any question, we can get back to you anytime, Prof. May ask.
Yeah. So
or you have the manual to use the software?
Okay, so we have a website. Then in the website, there is a forum page. So if you ask some question to the forum page, someone will answer. If no one will answer, we will answer.
Can you share to us the address of the website, Prof?
Yes, address of website. Yeah, you can find the address of the website on the PDF file I sent to you yesterday.
Oh, okay. Yeah. Actually, I have shared your lecture notes. Everyone can have a look on that one.
So please type IRIC, so you can find the website.
Okay. Is it answer your question, Dr. Yu?
Yes, thank you. I have another question. One last question lah. Banyak sangat tanya. Okay, Prof, I want to know whether Japan got your already have is it Japan have your own hazard map on debris flow? Have you developed the hazard map on debris flow in your country?
Sorry, I could not catch some word. So could you tell me again?
Hazard map.
Debris flow? Could you tell me again? Could you explain again?
Did Japan develop your own hazard map for debris flow?
Hazard.
Meaning that
Hazard.
you map the
Hazard map.
location of the debris flow.
Yeah.
Do you have
Hazard.
it in
hazard
Japan?
map.
Yeah, we have the hazard map of the debris flow all over Japan. Yes. So, but quality of the hazard map is very low. Yeah,
Because
so,
I wonder if you have the hazard map, why debris flow is still occurred and harm the public?
happen. Yeah, so so there is a hazard map, but the people don't use that hazard map. People don't believe that hazard map, so they don't escape so much. Yeah, so then because the quality of the hazard map is very low, so we try to modify the hazard map. So by use of this software, numerical analysis. So anyway, so yeah, so hazard map is already completed all over Japan, but still severe debris flow was happened and many people are killed by the debris flow every year. So yeah, so we have to change the hazard map.
Because when I saw from your analysis, I think that we can develop a hazard map from your analysis. So that's I wonder whether you have the hazard map or not.
It must be. Yeah, right. So you are right. So
I think.
But so so government has their own reason. Yeah, so then it will be changing year by year. So then maybe after 10 years, all hazard maps change to the new one by the numerical analysis, I think.
Because for your information, Prof, in our country, we still don't have the hazard map. So recently we have debris flow somewhere in Malaysia and somewhere in north of our country. So the government, our ministry, plan to develop the hazard map. So I think with the software that you introduce, we can develop the hazard map. But we need to get a training to run the software.
It's quite new.
Maybe we can collaborate so that we can develop our
own software,
yes.
our own country for hazard map, just like Japan, right?
Yeah, we can. Yeah, I can make a lecture how to use the software.
Okay.
Maybe for the next.
Thank you, Prof. I will contact you, Prof.
Okay. Next.
Thank you so much, Prof.
Yeah, thank you, Dr. Ayu. Next is Erizahan. Raise your hand, right? Erizahan.
Ohayo gozaimasu, Prof. Thank you very much.
Japanese.
No. I only speak very little. Okay, I'm the one who contacted you by email. Initiated the email. My name is Izihan.
Yeah.
Okay, thank you very much. In fact, by coincidence, I was trying to contact, I forget his name already, in DPRI, and then I contacted you. In fact, 2 years ago, I've already contacted someone in Hokkaido University. I think it's Kazutake Asahi. Yeah. So he, we were trying to work on this IREC with Nahrim. And then somehow we did not continue because of many issues, many reasons. So thank you very much for willing to. So by coincidence, I was very happy to look at IRIC because I did not expect you to present IRIC, and in fact you are one of the top researchers, developers in IRIC. Thank you. Okay, I have many questions in fact, so I don't think I post
never
them
mind.
here.
Yeah, never mind, Prof. Izan. You can ask.
It's okay. There's more. Some of them are more like comments and also to answer some of Dr. Ayu's concerns. I think the first thing is on hazard maps. Being hazard maps, we do not hazard maps do not really tell us when the hazard can occur, the disaster can occur. So it's just the maps are just to tell us which areas can be hit. But most of these areas are already populated, and in fact, for landslides and what I understand from your presentation, for landslides, they are very unpredictable. Can be from earthquake, and even from rainfall. You know, like you showed in one of your slides, it will occur after rainfall. You know, like people say, "Oh, the sun is already out, so we can go back to our houses." You know, so in these cases, the hazard map does not help at all.
Yeah.
Because they're already going back to their houses, then the landslides occur, and the debris flow occur. So that's an issue. We have the same issue here in Malaysia for flood maps, flood hazard maps. The government here in Malaysia has they have produced many flood hazard maps, but floods still occur. So now they're going into flood forecasting and so on. So there becomes a big research area in our country as well. I think it's in Japan. Okay, so that's the issue on the hazard maps. So on the model, I think you have shown the IRIC interface. To me is very impressive. It's already in GIS format, so you can already do everything on the GIS. You don't really need a separate user interface to go into the model and then to put in all the input values and all that. So that's good. And as I understand it, we have also other models. IRIC is like a big platform, and you have the other models that are being you can use in IRIC. So hopefully one day we can also develop a 3D. Because one finding which I've learned something new today from you is that debris flow is laminar, which is a finding to me, which is I did not know that. I suppose mud flow is more turbulent, but debris flow is laminar. That's good. So okay, so then we can probably look into more of the 3D part. One of the questions that I have is that how do you calibrate your model? Is it possible?
Yeah. So,
or do you need calibration?
So yeah, of course, always. So we will get the data from the field, or then so we check the flow depth and also the horizontal distribution of the inundation area. Or so then check the reproducibility of our model. So and also we check the reproducibility of the model by the Flume experiment. So in-house experiment, then check the reproducibility of the flow depth, flow velocity, and the concentration of the sediment. Then, so we are, of course, we are checking the reproducibility of the model. Yeah. Then, so and for the first question, so about the hazard map. So we are trying to suggest the easy escape method. So by using the flow characteristics of the debris flow or the flow characteristic of the water flow. So today I show you. So please go to the second stair. Okay. Not to stay at the first floor. Go to the second floor. So when heavy rain expected, please sleep on the second floor. Okay. Then please go to the 5 meter 100 distance houses or the other location. So during the heavy rain, they cannot escape. They will stay there. Ne? They believe nothing happened. They will stay there. Then had a disaster. So we are trying to suggest I'd like to suggest the easy escape method from the disaster. Okay, so by using our model, so then we would like to save the people from the sediment disaster or other disaster. Yeah. Something like that.
That's good. That's a good approach. One question. The other question I have is that I think most of the buildings and maybe houses as well in Japan are built for earthquake.
Yeah.
So that's probably why you can run up to the second floor and also hide behind buildings. Is that the reason? Do you think?
Yeah, yeah. No, yeah, there's a possibility of that. So, okay, but debris flow cannot break the building made by concrete. Debris flow can break the wooden house,
yeah.
but cannot break the concrete made house. So, maybe so concrete made house is constructed all over the world, so without any earthquake, then so that building will work in, of course, Malaysia, Indonesia. Maybe Malaysia has a lot of earthquake. I think so. Yes.
Yeah, we're starting to get some effects. But I think that's good. I think this is an area that we ourselves here in Malaysia, maybe in IIUM, especially in our department, we can do a research on this, on whether we can have the same type of condition where just run up to the second floor or higher, and also hide behind tall buildings, the taller buildings during such events. Because we had one, like Dr. Ayu mentioned earlier, one big, well, yes, considered big, and there was heavy rainfall on top of a mountain, and then the what we call, it's like a tidal bore or a tsunami wave that went down the mountain and then collected all the debris and caused considerable damage downhill. So that is one area that we're looking at in terms of debris flow. So I think you have the same as well. So I suppose your model morphed to
DH.
To DH can also do this. Yes, it should be able to handle a high column of water, although it's based on the shallow water equations as you showed. Yeah. Okay. The one other question, maybe final one. Coming to 11 now.
Please send me email.
Yeah, I can send you email later. We can communicate via other media. So just to, have you done any fluid structure interaction studies or research? Because we're also interested in the debris flow impact on structures in terms of like we saw earlier on the buildings, why they can you can go up to the second floor. So we are looking at fluid structure interaction. So it's more of the impact of the fluid or the hydraulic forces on hydrodynamic forces on the structures. For us, especially on bridges. So maybe we can collaborate on that as well. Thank you. Thank you very much. Arigato.
Okay.
Yeah, you know Malay as well.
Yeah.
Only thing, your opening slide is Selamat Pagi, not Selamat Tengah Hari. You have it as Selamat Tengah Hari, which is good afternoon.
Yeah.
Yeah.
Okay. Thank you very much, Irizan, for the questions.
Thank you.
Okay. Any other questions from the researchers and also the student? Student, you can ask any questions to our speaker. Actually, Prof, currently, for your information, okay, currently our research group are planning to prepare a proposal, okay, that related with the flood resilience, okay. So we have divided into 6 group, okay. We have a structure group, we have a material, geohazard group, we have a water, environment, and policy group. So each of the group need to come out with an effective solution, okay, in order to face with the effect from the flooding. So I hope that the output from this webinar can give us some ideas and knowledge in order to prepare the proposal, Prof. So maybe after this, maybe I can share your contact address, email, okay, to all the members, or anything they want to ask you, they can communicate with you, Prof. Is it okay for you, Prof?
Yeah.
Okay. Okay. So Any other question? No, eh? Okay. So, so we are heading toward the end of the webinar. Okay. So the Department of Civil Engineering, Kuliah of Engineering IIUM, wishes to express our utmost gratitude to Associate Professor Dr. Hiroshi Takebayashi for all of the invaluable knowledge and experience that he has shared with us today. So it is hoped that the knowledge gained from this webinar shall be instrumental in fostering a more meaningful connection between ourselves and environment, and also in conducting research and developing solutions that are beneficial not only to the Ummah but also to the global population at large, inshallah. So with that, let us close our webinar by reciting Tasbih Kifarah and Surah Al-As. Okay, thank you very much, Prof. Takebayashi, for your interesting webinar for today. Okay. Okay.
Arigatou gozaimasu.
Arigatou gozaimasu. Okay. Okay.
Yeah.
All right. Thank you, Prof. Okay, and
Bye.
then thank you to all the participants that for attending today's webinar. Okay. Thank you, Prof.
Thank you. Bye-bye.
Okay.
Thank you very much, Prof. Thank you.
Okay.
Thank you, Prof.
Okay. We will.
Taifa, can you ask the
Yep.
staff to wait? Okay.
Okay. Maybe after this, we can communicate, Prof. Takebayashi, after this. Okay, through the email. Okay, regarding to this matter. Okay. Okay. Thank you, Prof.
Hi.
Okay.
Bye-bye.
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 Okay. So, okay. So, the rest, you can leave this session. Okay, for the students. Okay, for the staff, please
Saya
remain
bangun
here.
sekejap, Ma. Saya
Okay,
bangun
bangun.
jalan
Silakan.
sekejap.
Boleh.
Okay, yalah, boleh. Okay, for other staff, please remain here because Dr. Khairah want to give a short briefing regarding to the pakar. Okay, so thank you for today.
Okay.
I will stop the
Student
recording.
Mahathir.